This is going to be, in a sense, a strange lecture. This is one of the, based on last semester, this was one of the hardest topics. So I want to make sure I cover everything, and going to throw in more information maybe than needed, but hopefully we'll get it. I just remembered to start recording this lecture, so that's done. I am putting them on my YouTube channel. I'll put a note on Blackboard with where to get the lecture videos. For some reason, I seem to have corrupted last Wednesday's, but last Monday's is in my YouTube channel, and this one will be as well. And if I can recover last Wednesday's, I'll put it up there too. I'll talk about the homeworks and stuff at the end of the lecture. I wanted to go ahead and get started. I know people are working on it. There's been a lot of activity on Slack and some other activity on other sources. And email is always fine. So we'll get to the lecture, and then I will, like I said, at the end of the session, I'll have time for questions or more details. So mutability, and particularly with respect to lists. Now, there's some strangeness, in a sense, with how Python works. So let me cut to pie chart and see if we can get it. This is the Monday, March 30th coding file. Here's some simple code for Python. And it works exactly like you would expect. A is 1, B equals A, that means B equals 1, B plus equals 1, so B is now 2, but we haven't changed A, so we'll just print the value for A, and A is still 1, which is what we expected, right? We assigned A the value 1. We didn't do anything else to change A, we just modified B. And so then we got the answer for A, that it was still 1. This is probably going to be a little surprising for a number of you. It's an interesting thing. I have C as a list, the elements 1, 2, 3, 4, the integers. Now I create another list, D. D is equal to C. And to D, I'm going to append the value 5. So D is now the list 1, 2, 3, 4, 5. Notice nothing up my sleeve. I haven't changed C at all, I think, but I'm going to print C, and I'm going to look at the result. And wait a minute, C is now 1, 2, 3, 4, 5. The question is, why did that happen? I mean, integers work the way I would expect, right? I set A equal to 1. I set B equal A. I did something to B, but not A. I printed A. A was exactly what I expected. It was 1. Here, I had a list. C was 1, 2, 3, 4. I set another variable equal to C, D. I appended something to D, but it apparently, when I appended D, 5 to D, this statement also changed C. So the theme of today's lecture is why that works. So let's go back to Chrome and start looking at these slides in more detail and figure out why. See if I can make this look better. This is happening. Okay. And the answer is that Python actually implements assignment statements different for different types of variables. Now, there are two basic categories, mutable and immutable variables. Now, the word mutable, and of course immutable or not mutable, are derived from the same root word as mutate. So think about things mutating. They change. These are things that change. So mutable variables can change, immutable cannot change. Oh, that seems weird. Okay. Immutable variables are the things on the left side of this slide. They're simple types. They're ints, floats, strings, booleans, none type, things like that. When I make an assignment, when I set B equal to A, Python just creates a new location in memory and copies the value over. B equals A copies the value of A into a new location labeled B. A and B are different locations in memory. They're different objects. And so when I change B, it doesn't change A, and A is immutable. Okay, that seems fairly logical. That seems to be how we would think this works. But on the right side, for other complex type, and so far we've only had lists, types that are built out of other types, Python doesn't do assignment that way. What Python does is it passes a reference to the original variable. So for example, I created a list, C. C equals a list 1, 2, 3, 4. C points to a location in memory. When I say D equals C, all Python does, it doesn't create a new location in memory and pass over the contents of C. All it does is it passes the same location in memory. So when C is a list and D equals C, C and D points to the same location in memory. This is an example of what's called a mutable variable. Mutable means can be changed. When I changed D, I changed C. So this is why, now I haven't explained why, we'll get to that in this lecture. I haven't gone into details of why Python does it this way. But for any complex variable built out of others, and so far all we've had are lists, when you set it, make an assignment like D equals C, it doesn't make a copy of the original variable. It simply points to the same location in memory. So now when you change either C or D, you're changing both, whether you realize it or not. This is, as you can think, a common source of errors in programs. All right. So we talked about the basic terms. Let's get into this a little bit more deeply. Now, immutable cannot be changed after being created ever for any reason. Let's look at that one in just a minute. Mutable. Mutable means it can be changed after being created subject to certain rules. Appending a value to a list mutates the list. It changes the list. So we can mutate a list. So does inserting a value, popping a value, or removing a value. Okay, so anytime we change a list by appending, inserting, popping, or removing, we're changing the list, but it's still the same location in memory. Okay, so we can change that. Let's go back and look at this immutable nonsense. This seems to be making less sense than ever. I'm claiming that an immutable variable is created, it has a value, and it cannot ever be changed for any reason. Seems absurd. What about the statement A equals A plus 1 or A plus equals 1? Doesn't that change the variable A? I mean, A was 10. A equals A plus 1. A is now 11. We mutated the variable. Not really. Different languages, different things. Here's what Python does. When you have an immutable variable, when you have a string, a float, an int, when you make it a statement like A equals A plus 1, what Python does is it actually creates a whole new object. It creates a whole new location in memory. It calculates the new value, and it stores the location, that value in the new location, and the previous object, the original location in memory of A, is destroyed. Okay, this seems bizarre. This is as you start to understand why this was the toughest lecture, the toughest topic last semester, and I think every semester. Why, when I say A equals A plus 1, do I create a new object and throw the old one away? Okay, let's go into it. I've talked a little bit, and now I want to explain the concept of a symbol table. in all computer languages, as you write programs, it creates what's called a symbol table. That is, for each symbol, each identifier, each name used in a program, it creates a table that has information about it. So, for example, if you use a as an integer, a equals 10, a equals a plus 1, it creates an entry. Python creates an entry in its symbol table, and it says, oh, a has been created. It is an integer, and it has an identity or a location. Now, this is generally a location in memory. This will vary on every different operating system. This will vary on every different version of the Python compiler. This will vary from program run to program run. So for now, we're not going to get wrapped around in this identity except to illustrate something. The numbers I put in this chart happen to be the locations in memory where these variables were put on my Windows 8 machine when I was doing some programming earlier yesterday. So when I created the variable a and made it an integer and assigned it the value 10, it was stuck in this location in memory 13662844464, and I don't really even know what it means. Python knows what it means, and it can get it for me. I created a string which held a name. I put the name in there and put it in that location in memory. I created a function called readFile, which I used to read in my CSV files when I was generating the real quick sample output for Project 1 that I just posted. And Python's created a location for that function and put it here, as you've seen in this symbol table. So, thing to remember, mutable, immutable, change, can't change, lists are mutable, or weird things happen. We'll talk about why when we get into it. Okay, but we have this table. It's created every time you use a new identifier, every time you use a new variable name, a new function name, a new whatever in a program, it creates an entry. When you change something, Python can update the entry. Now, on the bottom of this chart, I put something that's key. The symbol table doesn't tell you the value of anything. It just tells you where to go find the value. If you need the value a, the symbol table will tell you, go look in that memory location and you will find the value of a. It doesn't tell you anything about what the value of a is or even if a has a value. So we have this underlying symbol table running as we're working in our program. Now, Python provides a function, built-in function, ID. And the ID function basically gives you that value that's in the symbol table. It will tell you what the location of the identifier, of the variable name, of the function, it will tell you where it is. Okay, and so if we want to find out where A is, we can use ID. We don't use this in this class very often. I'm using this just to illustrate. I do not expect you to do any programming using the ID function. I do not expect you to do any programming using address locations or pointers or anything like this. Not in any homeworks, not in any labs, not in any projects in this class. I'm just using this to show that it exists and to illustrate what's really happening in memory. So it's a cool thing to play around with. A geek like me has fun. I can use ID and look at things. You're not expected to program with it at this point. It just is. It's just something that exists. It's a built-in function. Now, let's go back to PyCharm. Is PyCharm now being shared, or do I have to specifically click it?
It works.
Great. You never know with WebEx. I thought it works. So here, let's see. Where did I put this code in this thing? I'll just work through it directly. Okay, so A equals 1. Where is A? It's at that memory location because I'm on my Mac. I'm using Python 3.7 instead of 3.8. And the program is running this way. This is the location in memory where A is stored right now. Now, A plus equals 1. I just added 1 to A. Fine. A is now 2. But where is A? What's its ID? Notice it's moved. It specifically moved 32 memory locations down from where it used to be. That's a random coincidence. There's nothing particular about that. You'd have to look at how Mac did memory. So in this case, all I did was add 1 to A, and the purpose of this is to illustrate what I said. I had the original variable A. It had the value of 1. It was in the specific location in memory. When I said A equals A plus 1, it created a whole new location in memory for the value of A. It updated that symbol table. This location is now gone. I mean, this location still exists in memory, but it's marked as unused, available for something else. Okay? If I do it again, the same thing will happen. A plus equals 1. What's its new ID? And now it's moved another 32 bytes, 32 locations in memory. Okay? That's just, don't worry about the 32. There's nothing magic. It's just a function of how the Mac is working right now. This is what we mean by names, integers are immutable. I cannot change the contents of this location in memory. It has been created. It has the value 3. And I can't change the value of 3. I cannot mutate it. If I want to change the value of A, I have to create a new object and throw this one away. Floats and strings work the same way. Name equals the string Jones. Name has an ID. It has a location in memory. It's this one. Okay. I bumped up 224 roughly bytes in memory to put Jones. If I change that, name equals Smith, we can see that because this is a different value, this is now stored in a different location in memory. Again, string is immutable. When I change the value, it destroys the old object, it throws it away, it marks it as available, it moves it to a new place. Okay, let's go back to Chrome. So in this slide, we've seen the cases here where we have these things are immutable. Now we're going to look at mutable variables. We're going to specifically start playing around with lists. Okay? So back to pie chart. So we'll start with an empty list, and we'll see that it has a location in memory. Okay, whatever the Mac had available. Now we'll append a capital T. And we'll see that it's the same location in memory. We can mutate this variable. We can mutate what is stored in this location in memory because lists are different. The same thing will happen if I say x.insert. Let me append a couple of things first. I had it appended. H and E. And we'll see that IDX still has the same value. We can append everything we want. It hasn't changed it. But, and we also can do the same thing if we insert into element 1 the value R. X is now a list of 4 things, and it still has the same location in memory. So, mutable, immutable. Lists are mutable variables. You can change them. You can change what's held in memory. You can change the contents because Python allows it. Strings and integers and floats are different. Anytime you make a modification, it throws away the old thing and gives you a new one. I'm sorry, go ahead. Is your question?
Yeah, I just want to further understand. So a list, an empty list itself is an object, but when you have a list with variables inside, those variables are mutable. But you can't do x equals an empty list and then change x to a variable, because that would be immutable.
Right. You can't change. If you do a reassignment, let me see if I understand this. If I did something with X other than append, pop, insert, or remove, yes, that would force me to change its ID. That would destroy it. For example, X right now is the list T, R, H, and E. Suppose I said X equals the list A, B, comma, C, and D. Now I've changed X, and now you see X it has been removed. It's a new location. So if I understood your question correctly, when a list is mutable, so I can add, I can append, I can insert, I can pop, I can remove, and it doesn't change where it's located in memory. It changes the contents, but doesn't change where it's located in memory. When I do a reassignment, that changes where it is in memory. Did that answer your question, or did I misunderstood? Let's.
No, you got it. Just list as itself is a object, but the inputs inside can be changed. That's correct. Just wanted to make sure.
Yep.
Thank you.
Okay. Now, just to illustrate what happened in that part that was the surprising code, let's start with C. C is a list of 1, 2, 3, 4. D equals C. What's the ID of C? It's at that location in memory. What's the ID of D? It's in the same location in memory. And you can actually compare these. I can say ID C equal ID D if you don't want to compare long strings of memory locations. This is just going to give me a Boolean whose value is true. So this is why that surprising fact happened with this code up here that's in the top window. The reason we got that surprising result with the append was these two, when I made this assignment, D equals C, all that did was give D a copy of the value of C's location. It didn't separately copy over the elements. It just copied the location. The ID C and the ID D are different. So when I came back down and I said D dot append 5, okay, notice the ID of D is still the same value. It's still equal to the ID of C. They still point to the same place. And so when I look at the value of C, it's 1, 2, 3, 4, and 5, as is D. This is what we'd expect because they're the same location in memory. They're the same object. So the reason that this is happening is because lists are mutable values which can be changed. That's part of it. And also because when we make assignments of mutable variables, all we do is pass that location in memory. All we do is pass that identifier. We don't make copies and pass the individual values. Okay? As opposed to immutable types where we do things like this. When we made assignments, when we changed things, we move them in memory. We change the location in memory. That's why The immutable variables, the assignment worked like we suspected. The mutable variables, they work differently. So this is basically what I've done is worked through this particular slide to illustrate using the ID function exactly what's going on here. Okay, let's explore this a little more deeply because you weren't already hammered enough by this. I'm making the assertion that strings are immutable. But we've talked about how strings can be manipulated like lists, and lists are mutable. So why are strings immutable? Because strings are considered a basic type. Okay? And it turns out you can do things with strings. Strings are like lists as long as you don't try to change them. Okay. So many years ago, the Maryland Terps basketball team was coached by a guy named Gary Williams, and they won the national championship. And so people, as a joke, said Maryland is really Garyland because Gary is such a great coach. So let's define state to be the string Maryland. State is a string. And let's change the first letter of Maryland from an M to a G so we can indeed be Garyland. Lo and behold, we get an error message. The string object does not support item assignment. You cannot change the value of one or more letters in a string because a string is immutable, because a string cannot be changed after being created. I can reassign it. Okay, here's where state is in memory right now. I can change state completely. That's valid. And I can look and see that it has completely been moved in memory. It's now at a different location, just like immutable variables. A string, because of the way the people who design Python, and we will talk about why the people design Python this way, a string, you cannot change an individual element of it, but you can reassign the whole thing. Ah, you're saying, but wait a minute, we can look at part of it. We can look at state 0 through 4, which just gives us the first 4 letters of state. That's valid. And remember, with the slicing from last week, I can leave off the 0. If I leave off to the left of the colon, it's just going to start at the beginning. This is the equivalent statement. I can do that. I can look at an individual letter. I can slice and take a little bit, take other letters, substrings, okay? I can take 4 to the end, and it gives me land, okay? I can do that. Why can't I do the assignment? The answer is these things, looking at the values, looking at the first 4 letters of the string, looking at the last 4 letters of the string, they don't change the string. So the designers of Python said, that's okay. We will let you look at part of the string as long as you don't change it. Looking at things, we can access a string like a list if they don't change it, but the instant we try to change it up here by saying state sub 2 to 4 equals YL, that's an error because now you're trying to change the contents of an immutable type. So when we say strings are immutable, you can't change them. You can treat them like lists in a lot of ways. You can read individual letters. You can read slices of strings. You can read substrings. But you're only allowed to do that because they don't change the value of the string. They just access part of it, and that makes it okay. Okay. So we've been looking at huge, long integers that are locations of memory. Let's look at this a little bit graphically and illustrate again, demonstrate what's really going on. On the left, I assigned A equals 10. There was an entry in the symbol table created that says A is an integer, and it's assigned a location in memory. There's some 10-digit string that's associated with this. It's pointing here, and it has the value 10. Fine. When I said A equals A plus 1, A plus equals 1, what really happened in memory is that a new location was grabbed, 32 bytes away or whatever it happened to be. The calculation was done. 10 plus 1 is 11. The value 11 was stored in that location in memory, and A was marked with that one. So in that symbol table we showed you, that location, that identity column in the symbol table is updated, and it's now going to contain, and I got to remember, I've got slides up and can't highlight things. Sorry about that. The location in the symbol table is now going to take the location of this space in memory, whatever it is. Now, I've drawn a slash through the old, I've drawn a strike through the old location of memory, the old memory location of A. That is now gone. I mean, it's not really gone. You don't throw memory away. You just mark it as empty and available for later use. Okay? So that's what's really happening in memory when you do an assignment like A equals A plus 1. Python creates for immutable variables, Python creates a new location in memory, a new object. It updates its symbol table with this new mapping, and the old one is gone. It's marked as available for whatever use later on. For immutable variables on the right side, however, C equals 1, 2, 3, 4, we get a new location in memory. D equals C, D is assigned the same location in memory. So in the symbol table, C is a list, D is a list, and their identities will be the same. Now, if I did say, again, if I did come along with another statement that said C equals 5, 6, 7, 8, then indeed that would be thrown away and C would be given a new location in memory. But as long as I'm doing an assignment here, this is what's happening. It's the symbol table that's being updated because the new object is being created, the old one is being destroyed. Whereas with mutable variables, we're just actually changing the existing location in memory. We don't have to get a new one. All right, let's talk about language design. No, this is not on the test. It's not on the homework. It's not on the test. It's just a little bit of explanation. Pardon me, because I got a lot of questions about this last semester. Why on earth would you create a computer language like this? Why would you design something where some objects were immutable and you had to do a new copy of something to add one to it? The answer is because immutable objects, such immutable variables, strings, integers, etc., are much faster to access than mutable variables when the program is running. It's due to the architecture of the computer, and you have to take a 400-level class to get into the detail. But the bottom line is this. History has shown, and 60 years of computer architecture has shown, that when you have an immutable object created and never change it, it's much faster to access while the program is running than a mutable object. And so the result is that overall, if you have a lot of stuff as immutable, the program just runs faster. Now, if you're going to change those ints, those strings, those floats, it's much slower. You actually have to create a copy just to add one to an integer, as we've illustrated. Change an integer by 1, create a new copy. That's a pain. But a lot of experience and analysis of existing code shows us that lots and lots of time in coding, we never actually change an object. We never actually change the value of anything. We set a value once, and we never actually change it. This happens often enough that it becomes faster to just design the language this way. This is a decent design trade-off. Now, again, that's not on the test. That's a 400-level concept as to why. But I did want to explain because it seemed a natural question to me, and in fact, I got a a lot of good questions like this last semester. Why on earth it works this way? Why would anyone ever design a language where you have to make a copy to add one? The answer is because overall it's better for program performance. Okay, don't forget, but it's a question. Go ahead.
Yes. So just wondering, are lists the only mutable variables that we're going to be dealing with?
No, we will be talking about dictionaries on Wednesday.
Okay.
In this class, we will do lists and dictionaries.
Okay, one more thing.
Yep.
If we want to use a list like we would a variable where we just want to set another thing equal to it, but not change the original, can we like literally make a copy of it instead of just assigning it?
Oh, what a great question. Yes, we can, and we will talk about how to do that. And in fact, we'll talk about two different ways to copy it. So yes, that's a great question, and the answer is yes, we can, and we'll talk about exactly how to do this. This slide just summarizes again, hammers home. This you do need to know. Immutable objects, int, float, Boolean strings. Don't worry about tuple and Unicode. We haven't gotten to them. We may at the end of the class. We may not. Okay. Mutable objects, lists, dict, D-I-C-T is short for dictionary. That's a typo. We don't have class on Thursday. We're going to get to it on Wednesday. And set, we may or may not get to in this class. These are the ones that are defined in Python. So we are going to get to dictionaries on Wednesday. DICT, dict is short for dictionary. That's the other mutable. The immutables are there. This is something you need to know. This is something that will pop up because it impacts your programming. It'll be on tests and stuff like that. The things we haven't covered yet, tuples and Unicode and sets, you don't have to know, but the rest of it, this would be good to know. Before we get to how to solve the problem, there's one more thing I want to talk about, which is when you pass a list to a function. Now, on the right, we have the main program. We set a list to the value, the list 1, 2, 3, 4. We call the function, strange stuff, with the parameter main list, and then we're going to print what main list looks like after we get back. Okay? So on the right side, we just set the main program, initialize a list, call a function, print out what the value of the list is. On the left side, we have a function. Now, again, hopefully everybody's starting to get a good grip on what functions are. Def means, here's a function called strange stuff. Its parameter, I misspoke a minute ago. A list in the function definition is the parameter. On the right, strange stuff at the call main list is an argument. It's not a parameter, it's an argument. I misspoke. Main list is the argument. A list is the parameter. I append the value 5 to the list, and then I return. Now, I have a return statement which returns nothing. It doesn't return any value. Okay? That's the same as returning none. So the function strange stuff returns the value none of type none type to the program, the main program. Nothing should happen when we get this back. Let's go to PyCharm, and I think I actually did put this in the code. Hopefully, yep, here it is. Here is my function. Here is my main program. Okay, main program calling the function. Lo and behold, this print statement, main list, shows that we've added 5, even though the function call returned nothing. I didn't return a modified list. So how did this happen? The reason is this. Remember that when you have an argument, this is the argument in the main program, it maps to the parameter, a list. Because this is a list, because this is a mutable variable, we didn't make a copy of main list in the procedure, in the function, rather. We did not make a copy of main list in the function. We actually just passed the location in memory of the existing list. Sorry about that. That particular dog doesn't like trucks going down the road. Matching arguments and parameters Matching arguments and parameters works the same as assignments. You don't make a copy of the value and just deal with a copy. If it's a list, what you do is you just pass the location in memory. So when we changed a list up here, it was the same ID, it was the same location in memory, and so that's why this function, which didn't do anything apparently and returned none, that's why it actually changed the stuff, the value of the argument in the main program. So this is another case because matching arguments with parameters is the same as just making an assignment, and so that's why this happened. We got the same location in memory. When we changed one, we changed them both. This works because of the scope rules. The main list variable is defined in the main program. So it is accessible globally. Any and all functions can access this location in memory from the main program, whether we declare it or not. If we had done something from the function by scope rules, the main program couldn't mess it up. But because this is defined in the main program, we could mess that up with the function by doing something in the function. Okay? Because the mapping that argument to the parameter is the same thing as making an assignment. So, next question is how and why. Another thing on why that the parameter argument mapping happens because the lists are mutable and it works across function calls. Why? Guido van Rossum, a Belgian, is the guy who originally wrote Python, and it's that way because he wanted it that way. If you write the language, you get to decide how it works. And enough users agreed with him that it was decided this should be the way function calls work. Okay. So now, how do you do it? There are two ways that will work to make a copy of the list so that you will not mess with the original. The function list is called the constructor. It's one way we create a list to begin with. Okay, so if we go back to PyCharm and come into the console, if I say my list equals list of 1, 2, 3, and 4, this constructor okay. Where did I miss this one? Hang on. Okay, let's go with this one. I'll get into that one in a minute. Okay, I can create a list of things by using the function. Let's go to the list operator. And if I use that, it creates a new list. So this is what I wanted to do. Okay. So my list equals 1, 2, 3, 4. It has an ID. Now when I say new list equals make a new list based off of my list, if I look at the value of new list, it has the same value. It's 1, 2, 3, and 4. It's the same. But now if I look at the ID of new list, I can see it's a different location in memory. ID of my list, we can see this, but just to double check. New list and my list are now different places in memory. So if I use the list constructor, now if I say new list dot append 5, new list is indeed 1, 2, 3, 4, 5. My original list is only 1, 2, 3, 4. So the answer to the question from a little bit ago is here is one way to create a copy, a true copy of a list where we can modify the copy, we can modify the new list without having to worry about the original. The original is protected. We're not messing it up. We've created a true copy. That is using the function, the list constructor. Sorry. That is using the list constructor. We can also use a slice of the a slice technique. So in other words, I have my list 1, 2, 3, 4. It has an ID. Okay, fine. Now another list equals my list colon. This is a slice. It says go from the beginning to the end. In other words, just take the whole list, because all I have is a colon. Nothing before it means start at the beginning. Nothing after it means go to the end. Take a slice consisting of the whole list. Now I look at the value of another list. Indeed, I got all the elements 1, 2, 3, 4. If I look at its ID, I see yet again it is different than my list. It's also different from new list that we had up above. Okay? So those are two choices. Those are two options you have when you want to create a copy of a list so that you have a true copy and you do not mess with the original.
A quick question.
I'm sorry, go ahead.
So basically, you don't need to worry about creating a true copy of a list unless you know that you're going to need to be modifying that copy. If you're just using that for like comparing each value to something else, then you just do like a shallow copy.
That's correct. That's
Okay.
correct. Now, we do want to talk about this term deep copy and shallow copy. These two methods, using the list and taking a slice, works fine if it's a list of basic types. If you have a list of integers or a list of floats or a list of strings. But what if it's a 2D list? What if it's a list of lists? And so I've got an example here. A is a 2D list. We talked about 2D lists last week. It's got a list of 3, a list of 3, and a list of 2, because that's 8.9, not 8,9. So that's our list A. Now I'm going to create B is list of A because I want to create a copy. But this just creates what's called a shallow copy of the list, ID B equal ID A. That's false, right? B is a different location in memory. But what if I looked at the constituent parts? What if I looked at the internals? What if I said, how about B sub 0, that list 1, 2, 3, and compared it to the ID of A sub 0? What if I compare the list 1, 2, 3 in B with the list 1, 2, 3 in A? Well, I know that B and A are different locations in memory. I know that they're different objects. But what about internally? Guess what? Python is lazy, like a lot of languages are. And so that location in memory that has B, we didn't copy the 1, 2, and 3, the 4, 5, and 6, and the 7 and the 8.9. So if I do B sub 1 dot, let's put the dot outside the square brackets, append 10. Now let's look at A. And look at this. We have modified one of the elements of A because this is called a shallow copy, not a deep copy. That is, we just copied at a high level the entire object. The internal parts, the lists that make up the 2D lists, are actually the same between A and B. So if I truly want, if A and B are made of lists of simple things, they're lists of strings, they're lists of ints, they're lists of floats, this is never going to be a problem. Either deep or shallow copy will work. We're good to go. If I'm not going to modify it, then it doesn't matter. The shallow copy is perfectly fine. If this is a list of lists, if this is a 2D list, and I'm going to modify it, then I need to protect the original so that I don't change it. Now, the interesting thing about that is I could change a component of A by changing this, but what if I said B dot append the list of 1 and 2? Now, here's B. I've added a fourth row. I've added a fourth row to B with this B dot append. What's A? A does not have the new element. This was the element added to B. It was not added to A. Yet when I looked at this with this append, I could change the component in both B and A. So this is one of these kind of bizarre things, and this is when you hear the term deep copy and shallow copy. The true meaning is I want to make a true copy of an object, a list, so that I don't change it unintentionally. When I change the copy, I don't change the original. For most things, this copy statement using list or using a slice is perfectly fine. It will work for you, and you're good to go. But if you have a list of lists and you truly want to protect them so that you truly don't change any component of the original when you change the copy, then you need what's known as a deep copy. And the way you have to do that is you have to apply this list or this slice to each element. To get a true deep copy of A that could never be modified by B, what I would have to do is create B as the slice of each. I'd have to do each component one at a time. So when you hear the terms deep copy versus shallow copy, a deep copy is you make a new copy, a new valid copy for every element of the original list. All right. This is in words what I said, so let's make sure I got it correct. A shallow copy, it's a different location in memory. ID of B is not equal to ID of A. We showed that. But the components are in the same locations, so ID of B0 equals ID. This should be A0, not ID of B1. That's a typo. My apologies. This should be ID of B0 equals ID of A0, etc. That's what that truly is supposed to say. So you can still have unintended side effects. To make a truly independent copy, you need a deep copy. All right. So, last slide. I have hit you with what is a really, no pun intended, deep topic that is very difficult to understand, that causes a lot of programming problems, and that caused last semester's students, the majors and the non-majors alike, the most problem. And so what I've tried to do is come up with a way where it can, I can explain what's going on. In terms of the words themselves, a mutable variable can be changed after its creation. That's a list by popping, appending, removing, inserting. And we'll talk about dictionaries on Wednesday. Immutable means it cannot be changed after creation. And that's an int, a float, a string, a Boolean. And the reason that applies is that even if we add one, we have to make a copy, we have to create a new object. Okay. Those are the things that we've covered so far. What's really important and what you need to take away from this lecture is they behave differently when you make assignments. The third bullet on this slide is the one thing I want you to take away from this lecture more than anything else. If you take away more, that's great, but this is the one point I really, really want you to get. Mutable variables and immutable variables behave differently when you make assignments. When you make an assignment to a mutable variable, if C is a list and D equals C, you can change that value without meaning to, because you can change it and Python doesn't care. It presumes if you change it, you wanted to, you can change it without meaning to if you're not careful. The way assignments work with immutable variables, with ints and strings, is when you make assignment, it's like anything else. It makes a copy, it creates a new object, and you cannot accidentally change the original. It's not possible to accidentally change the original. The way you work around it, the fourth bullet on this slide, is if you want to avoid unintentionally modifying a list, you have to make a copy of the list and work with that. If it's a simple list, a list of ints, a list of strings, a list of whatever, just either use the list constructor or the slice. Either one of those will work perfectly. You're good to go. If it is a 2D list, if it is a list of lists, then you have to make a copy of each component. So, like I said, this is a pain in the neck topic. It is one of the hardest things we'll cover, and I went fairly fast, but I hope that you got things out of that we can build on. I've got 20 minutes left. I want to talk a little bit about the project in the lab because there were some issues about the lab last week. I do want to talk about that. Before I get to that, are there any questions on the lecture?
I just have a quick question.
Sure.
Could you demonstrate how to deep copy a 2D list?
Sure. What I would do is I would have a copy. I would make a copy of each one. So let's go back up here with A. Let's assume A is my 2D list. Okay. To make a deep copy, I would say for I in range of the length of A, so I'm going to do each component. This is not going to work because I did not create B as a list first. Hold on just a second. Let's see. Trying to figure out if there's a way I can save it. I don't think so. Just die. Okay, let's try this again. I have to create B as a list first. This is why the previous one would not work. I couldn't have been. For I in range length of A, that's how many rows. B dot append list of A sub I. Now, if I look at B, it's the same structure as A, but now if I look at ID of B sub 0 and compare it to ID of A sub 0, if it doesn't make a liar out of me, this should be false. And it is. How about that? It actually works. So that's your answer, is you have to go through and do it in a loop like that, copying each element and using either that list constructor or taking the slice of each of the elements. That's how you would do it. Okay? All right. So if there are no more questions, just to give you a quick heads up, it's not quite 5 o'clock. Sometime before 6, I will post lab number 7 on GitHub, and I will also make a note on the assignment section of Blackboard, both of those. I will take care of both of them for lab number 7. You will have till midnight Thursday, the 2nd of April, to submit it. Lab 7 is straightforward. I unfortunately don't have it on this computer. It's on the wrong laptop, so I can't display it. but it is fairly simple. I give you a 2D list, and I ask you to type in, it's basically the first 5 rows of one of the data files of the project, not separated by commas, separated, as values. And I ask you to first create a 2D list by typing in the values or copying them from the assignment. So that's step 1, is you'll create a 2D list. The second part of that is you will access individual elements of that 2D list. And remember, you do that by using sub-row, sub-column. So I'll ask you, what is the third element of the 4th row? What is the first element in the 2nd row? And you will real quick, put print statements, list sub 1, sub 2, or sub 3, sub 4. So that's the second thing you'll do. The next thing is you will access a row. Now remember, with 2D lists, you can access an entire row at once, because if you just give one subscript, you get the whole row. You get that whole list. So that's a one statement, print out a row. And then append a row, you will do that. Then I show you how to add a column. Now remember that columns from last time, you cannot insert a column with a single statement. It doesn't work that way. It's row major order. Rows come first. And so in the lab, you will write a real quick for loop to insert a column, and I actually give you the for loop to model from. The only thing you'll do is change a couple of values in the for loop, and you will insert a column. And that's all you have to do for this lab. So all I wanted to get you do with Lab 7 is get you comfortable with 2D lists. You'll create one, given values I tell you what they are. You just have to type them in. The only thing you can do is mistype, and then you can fix your typo. The second thing is you will access an individual element. The third thing is you will access a row and then append a row. And the last thing you will do is insert a column, and you'll have to insert the column by going row by row to insert an element at a time. That's Lab 7. You have till midnight on the 2nd of April, which is Thursday night, to submit Lab 7. And as I said, I will post it by 6 o'clock tonight. I just have to double check to make sure I don't have yet another typo. That is Lab 7. On the project, I finally got around, my apologies, to posting a real quick sample output, and I also realized that when I posted it, I don't have the modes. I have the values I got for medians, means, and standard deviations of 4 data sets. I printed them out labeled as such. Modes are a little bit more awkward because there's more than one, right? There's not a single value that appears the most times, so you'll have to, as your modes, print out one of the values, which is the mode, and that's good enough. I didn't print that out. I'll fix that. So you will have the things to compare with. I have extended the deadline for the design till Wednesday night. You have till midnight Wednesday night to submit your design. If you already have it done, please go ahead and submit it, because I've asked Jordan and Anna to look at them and try to give you feedback on your design as quickly as they can. The earlier you get it to them, the earlier they get it back to you. So if the design is done, get it in. If you haven't done it, please work on it. You now have till Wednesday night. I've extended the deadline. I've been talking to students and emailing back and forth and what have you. I understand the issues. I understand this is not an ideal world. We didn't, design this as an online class, but we'll get it done. The actual program itself is still due next week. When you have lab tomorrow, whether you're Anna section 11 or Jordan 11:30 or Jordan section at 4, you can go on to Discord, ask questions to them, and what they do is they take you into a separate room, logical room on Discord, and they can talk to you. They can exchange either VoIP. You can either speak by voice if they have capability, or you can, chat back and forth via IMs. If you need help with the labs, they will work through. They already have copies of the labs for reference. You also can ask any of the other TAs who have office hours. I believe the office hours are 10 a.m. to 5 p.m. Monday through Friday. You can ask the other TAs if you have any questions. Now, I'm trying to make all of the TAs in the majors classes aware of our project, which is a little different. They all have the skills to do it. It's all Python. They know how to program. They should be able to help you if you have any questions. So if you can't get to Anna or Jordan, it should not be an issue. You should be able to get help from any other TA. If you can't, let me know, because I talk to them all on a regular basis.
Professor?
Yep.
Could you post the link to access the office hours?
I will do that. You should have gotten an invite to join Discord. If you did not, let me know and we'll get you one.
But is it like a different link for every TA or?
No. What happens is you go on to Discord. Let me see real quick. What's the easiest way to get to Discord from here? I don't think I have the thing saved, but I can be able to get to it. Get to it this way. This be the easiest way to do it. Okay. Great. I don't have my password. I apologize. I have to fix it. I've been working at Discord off my other laptop. I will send you a link and we'll get this fixed. Getting back to what happens is when you get into Discord, you will see a number of channels. One of them is called questions. If you don't see your TA listed, you will see on the left side of the screen a list of the TAs and instructors, myself, Hamilton, or Johnson, who are currently logged in. So you can directly ping the one of the TAs or myself if we're logged in at the time, or you just go into the questions channel and write down, I have a question. And one of the TAs will respond, and you can ask if Anna or Jordan's around or whatever. It's the like I said, it's just the Discord server. And if you did not get an invite to set up an account on Discord, let me know, because we do have to get that fixed and get you on there. Okay?
Professor?
Anything else on that?
Yes, I have a question.
Yep.
So on the project, you said for like the median and the mode to make a local copy. Is what we learned today what you meant?
That's probably appropriate, because if you calculate the median or mode directly from the, you're going to read in the file, and when you process the data in the file, you're going to create lists. If you do calculations, let's say you do median first, and you do some calculations on the list, and you change the list, you may make it impossible to calculate the mode. If you do the mean first, you may make it impossible to do the median. If you do, so yeah, if use the techniques from today to make a local copy so you don't accidentally change the values and thus get the wrong answer when you do the mean first, then the median second, then the mode, or whatever. Yes.
Okay.
And since they're all lists of integers, right? They're simple lists. Use either the list technique or the slice technique, and that will be perfect for creating your local copy.
All right. Thank you.
Okay.
Go ahead.
Go ahead.
Okay. So, is there? Do you upload the audio from?
Yes, I do, and I will post a notice on the Blackboard of where my YouTube channel is. As I said, last Monday's lecture is already out there. I apparently messed up Wednesdays. I'm still trying to recover it, but this will be put out there in the next 20 or 30 minutes, or presuming my internet connection holds up.
Thank you.
So you will be able to go out to I'll post the link, but just my name, Alfred Arsenal. That's the YouTube channel, and that's what you'll find out there. And I took the dance videos down. Right now, there's no dance videos. I may put them back up, but there's not there now. But yeah, that's where you can get that's where you can get all the recordings of all the lectures. Okay. Any other questions?
Yes. In terms of the create list project function,
Yep.
it's supposed to output 2 lists, but so is that supposed to be like a list of lists, or are we just can we just break that up into 2 separate functions, one for projects, one is for exams? Because these 2 variables.
You actually have options. When I made the assignment, we had not covered 2D lists. So it is perfectly acceptable for you to create a set of 1D lists. So for example, one list of all the project 1 grades, one list of all the project 2 grades, one list of all the project 3 grades, and those are all 1D lists. That's perfectly acceptable, and you will get full credit if you do it that way. That's why it would say more than one list. If lists of projects, lists of tests, whatever. If you want to, if you feel comfortable enough with 2D lists that you're willing to go ahead and take a crack at creating the 2D lists for an entire class, then you really only need to create that one single 2D lists and you're okay.
Okay. And one other brief little point. So it was a little unclear to me how the create list was supposed to function. So are we just making a list of of each project scores for each student, basically just breaking that up? Or are we summing the 3 projects together and writing that score for each student? And same for exams.
Former is easier and it is acceptable. I would do that. If you want to sum the 3 project scores, you can do that.
It was just not clear how it was written. That's all. I was just wondering.
Oh, no, that's okay. I accept that. I mean, as I said, I find when I rush through things, and unfortunately sometimes I do have to rush through things, I'm not clear. So that's why we're here. Ask all the questions you can. Let's get it clear.
All right.
Okay?
I have a question.
Sure, go right ahead.
So where did you say you were gonna post the audio for this lecture?
I have a YouTube channel that's under my name, Alfred Arsenault. I will post the audio from today in a little while, and then I will post a link on Blackboard that tells you where to go on YouTube. The actual, I don't know how to post audio recordings on Blackboard, so I'm going to post them on YouTube. And I will post a link on Blackboard in an announcement that says, go here for my YouTube channel. If you actually go to YouTube and search for my name, Alfred Arsenault, you may be able to find it now without the link, but I will post the link.
Okay. Thank you very much.
No problem. Okay. Anybody else?
Yeah, I have a question.
Sure.
Just to clarify for the project, at the end of each file, we're supposed to have 6 lists in total. 3 for project and 3 for test.
You can do that. That is acceptable, yes. Yes.
Okay, thank you.
Yeah. Again, if you feel confident enough with 2D lists, since we have covered them in class, you are free to go ahead and do this as a single 2D list and change the assignment a little bit, but you don't have to.
I had one question about the project.
Sure, go right ahead.
In the project file, it says that there's supposed to be 12 functions, but when I actually write them all out, there's less than that.
There's 8, and that is a typo. Yes,
Okay.
I have exchanged even messages with several classmates already. Yeah, I think if I remember right, there's only 8 in the assignment. There's not 12. That's a typo.
Yeah, there was 8 when I did it. Okay, thank you.
Good.
I have 2 questions.
Sure.
One, you said that you'd be sending out an output. What's it called? A sample output for us?
I posted that on Blackboard shortly before this class started, and I will also post that on GitHub. But it's on Blackboard now.
Okay. And one more thing. So you just said that the 12 functions was a typo.
12 is a typo. I think there are only 8 in the assignment.
Yeah, there were only 8, but I took that as in you wanted us create 4 other functions.
You You will. That's not wrong. That you don't lose any points for doing that, but you don't have to. The 12
Okay.
the 12 is simply a typo on my part, for which I apologize. I mean, you are going to have to probably create some other functions, right? You know, if you do it with just those A, it's going to be interesting to see how you pull it off. But the 12 is a typo. It should have said 8.
Okay. Thank you.
Okay,
I have a question.
sure.
About homework review. So for me, I'm using my homeworks as a guide for my project, and I don't have any feedback.
Yep, and that's because I'm an idiot. No, the true answer on homeworks is because I was supposed to create a whole bunch of files that would allow the TAs to grade them, and I have not yet done that. I am working as fast as I can. So we apologize that you have not gotten feedback from homeworks 2 through 5. We're working on that. That's on me.
Well, will there be a review at all? Like, could I guess speak with the TA to go over if I missed the homework too? Could I just go over a review of the whole?
Certainly. Talk to the TA, and they will be able to help you with anything. They just haven't graded it yet.
Okay.
Okay.
Thank you.
Yeah, and this is a side note, but next Monday's lecture, by the way, the exam is next Wednesday. Next Monday's lecture is an exam review. We can also talk about other programming reviews as well then. Okay, anything else? We are now at the end of time. Thank you very much. I will talk to you on Wednesday, and I will get the announcements of this up as quickly as I can. Thank you.